Okay, so we were discussing homework 7 from the game theory section last time, and we had went over problems 1 through 4. So let's discuss the remaining homework 7 and some part of homework 8. Um, Question 5 is pretty similar to question 4, so I'm not going to go over that. I'll let you try that for yourself. Let's go over question 6. So you're given this payoff matrix for a two-player game, and both the players have two strategies each. Now, before we move on, I would like to discuss a shortcut method to find Nash equilibrium. So a shortcut for Nash equilibrium involves two steps. So you first circle the maximum first numbers for each column. And by first numbers, I mean the payoffs for player 1. So the first entries in each of these boxes, right? So let's see why we do that. Okay, so let's look at the first column, column X, or the case when player 2 plays strategy X. You circle the maximum first number. So between 4 and 1, the maximum is 4. So you circle that. And now, what does this tell you? This basically tells you that if player 2 plays X, then the best response for player 1, if player 2 plays X, is A, right? Because if player 2 plays strategy X, then A is the one that gives player 1 the highest payoff. This is what we are basically doing when we are looking at the first column and then circling the maximum first number, right? Let's do the same thing for the second column this time. So look at the column corresponding to strategy Y, and now circle the maximum first number in this column. So between 3 and 0, 3 is the maximum. So you circle that. Now what this tells you is that the best response for player 1, if player 2 plays strategy Y, is A. Again, this is because we're looking at the column, the highlighted column Y, which corresponds to player 2 playing strategy Y, and then circling the maximum first number means looking at the highest payoff for player 1 in this situation. And then that would just mean that A is the best response for um, Y. Okay. Now let's look at the second step. So that involves circling the max second number for each row. And by second number, I mean the payoffs for player 2. So the second entries in these boxes. Okay, so let's look at the first row corresponding to A. Now circle the maximum second number in this row. So the second numbers are 3 and 4. Circle the maximum, that's 4. What does this tell you? It just tells you that if player 2 plays strategy, sorry, if player 1 plays strategy A, then the best response for player 2 is Y. Similarly, look at the second row corresponding to strategy B. Look at the second numbers, -1 and 2. Circle the maximum, that is 2. And this tells you that the best response for player 2, if player 1 plays strategy Y, is B. Okay. Now, how can you use this to find a Nash equilibrium? So the key here is that Nash equilibrium occurs for an outcome when you have two circles next to each other in the same box. So in this case, this box here has two circles next to each other. So this outcome, which corresponds to A and Y, is a Nash equilibrium. And why is that? Because they are best responses to each other. You see that A is the best response to um, Y, and Y is the best response to A. Okay. So this was about a shortcut to find Nash equilibrium. Now, how do you use this to quickly solve problem 6? So it asks you to change just one number in this payoff matrix so that AX becomes a Nash equilibrium. Now let's just copy down the actual original payoff matrix first without changing anything. And you know that when you circle the first numbers, the max first numbers for each column, you get 4 and 3. When you circle the max second numbers for each row, you get 4 and 2. Now, in order to have AX a Nash equilibrium, you want the two circles next to each other in AX, like the box corresponding to AX, which is the first box here, okay? So how can you make that happen? You can make that happen when you have this max circle for the second number in this row here instead of here, right? So instead of 4 being the maximum, this number must be a maximum. So how can you do that? You can just replace 3 by something that's bigger than 4. So let's say 5, right? So you can change this matrix in a way that now AX is a Nash equilibrium. Okay. You can also do the same thing by changing one different number. So again, let's have the original payoff matrix. And let's circle the max first numbers in each column. So 4 and 3 again. Max second numbers in each row. So 4 and 2. Okay. Now, again, you want this circle here because you want AX to be a Nash equilibrium. One way was that the one we discussed in part A, where you can increase this 3 to a 5. Another simple way is that you can decrease this 4 to something that's smaller than 3. So make this, let's say, a 2, and then the circle now goes to 3. So again, AX is a Nash equilibrium in this case. Now let's move on to homework 8. Now the first question involves, I think, 4 games. All of these, you can read the games are pretty interesting, but you can also just start by looking at the payoff matrix and just filling out the answers. You don't really need to read the entire paragraph, but it's interesting to do so. So I suggest you go with these games. But for now, let's just look at the payoff matrix. This problem is pretty similar to one of the problems we did on homework 7 that we discussed yesterday. So I'll just do one again for a quick recap, and then I'm sure you'll be able to do the remaining parts for the first question. So let's do this first part, okay? Now, for the sake of simplicity, I'll just call boxing match B and dance D. Okay. Now, let's look at B1 of boxing, which means that when person 2 decides to go for the boxing match, what is the best response for person 1? So look at the column corresponding to boxing match for person 2, and then look at the highest payoff for person 1. So compare 4 and 0, the first numbers, which are the payoffs for person 1, and then 4 is bigger than 0. So this corresponds to the best response for person 1, given that person 2 decides to go for the boxing match. So best response for boxing is boxing. Similarly, let's look at the situation when person 2 decides to go to the dance. So this column here. And now we're looking for the best response for person 1. So we're interested in the payoff for person 1, which is given by the first numbers in these boxes. So compare 0 and 2. 2 is the bigger payoff. That means that this outcome is, or like this strategy is the best response for player 1, given that a person 2 decides to go to the dance. So best response to dance is dance. You would see that this situation is symmetric. So yeah, you'd again see that the best response for person 2 and person 1 decides to go to the boxing match is again boxing match. And then same for dance. Okay, now let's see if you have any dominant strategies for player 1. So we're looking at this data here. So there are no dominant strategies for player 1 because there's not a single strategy that works for every opponent strategy. So if we had boxing here, then boxing would be a dominant strategy for player 1. If we had dance here, then dance would be a dominant strategy for player 1. But since you don't have one single strategy for player 1 that is the best response to each of the opponent strategies, there's no dominant strategies for player 1. Okay. Similarly, you look for dominant strategies for player 2. That means you're looking at this box here. Again, there are no dominant strategies for player 2. Now, social welfare maximum strategies would be the ones corresponding to having the highest social welfare. And social welfare is just the net payoff of each outcome, which means that the sum total of the payoff for all players. So social welfare for the first outcome is 6. The second outcome is 0. Third is 0. Fourth is 6. So clearly, 6 is the highest social welfare, and you have two outcomes that correspond to that. One is boxing, and another is dance. Okay. Now let's look at the Nash equilibrium. Let's use the shortcut that we discussed to find the Nash equilibrium or Nash equilibria if there are multiple. So again, circle the maximum first numbers in each column. So look at the first column. Look at the first numbers in these columns. So 4 and 0. Compare 4 and 0. 4 is the bigger number. So you circle 4. Now look at the second column corresponding to dance. Look at the first numbers 0 and 2. Circle the maximum number. That's 2. Now you look at the first row and circle the max second number in this row. So compare 2 and 0. So 2 is the bigger number, so circle that. Finally, look at the second row and compare the second number. So compare 0 and 4. You see that 4 is the bigger number, so you circle that. Now, Nash equilibrium is when you have two circles next to each other in the same box. So you have that with this outcome as well as this outcome. So you have two Nash equilibria, BB and DD. So this is not always the case, though. Your social welfare maximum strategies don't always coincide with the ones giving you a Nash equilibrium. Okay. And please go over the remaining problems yourself. They're pretty similar. Now let's look at question 2. Question 2 and question 3 are again very identical, just that question 3 has a fourth part that talks about rational outcomes. So I'll talk about question 3 because it also covers question 2. Okay, so you are given a payoff matrix. So this is a 3 by 3 matrix, meaning that there are two players. Each player's each player has three options or three strategies. And now you want to find all dominance relations. Now, let's talk about that. So whenever you're looking at dominance relations, see that you're comparing strategies for a fixed player. So player one has strategies A, B, and C. So you can compare A, B, and C, meaning that you compare A with C, oh, sorry, A versus B, B versus C, and A versus C. Similarly, you find dominance relations for the strategies for player two, meaning you compare. Let's have this in a different color. So meaning that you compare strategies for player two. So compare X, Y, Z. That is X versus Y, Y versus Z, and X versus Z. Okay. So let's compare A and B first. So you look at the first row and the second row. And now, in order to compare which strategy is dominant, since these are strategies for player one, you would compare the payoffs for player one, which would be the first numbers in these boxes. So compare 4 and 4, they're equal. Compare -2 and 1 is bigger. Compare 2 and 3 is bigger. And you can also circle this 4 because it's bigger than or equal to the 4 above. Okay. So this means that B dominates A. It doesn't strictly dominate A because in this case, when player 2 plays X, both strategies A and B are the best responses. So yeah, in one situation, A is as good as B, but in all the other situations, B is strictly better than A. So this is how you denote that. Now let's compare B and C. So you're looking at the columns, the rows corresponding to B and the row corresponding to C. And again, compare the payoffs for player one. So compare the first numbers. Look at 4 and 5. 5 is bigger. Look at 1 and 3. 3 is bigger. And look at 3 and 6. 6 is bigger. And each of these numbers is strictly bigger than the ones in row B. So C strictly dominates B, right? Now finally, let's compare A and C. So look at row A and look at row C. Compare the payoffs for player one. So compare 4 and 5. 5 is bigger. -2 and 3. 3 is bigger. 2 and 6. 6 is bigger. So again, C strictly dominates A. And I needed to have this in pink. Sorry. Now let's compare strategies for player 2. So let's compare X versus Y. So you look at the columns for X and Y. Now this time you're looking at strategies for player two. So comparing two strategies for player two would involve comparing player two's payoffs for those corresponding strategies. So payoff for player two, they are uh, encoded in the second numbers in these boxes. So you compare those. So between 4 and 8, 8 is bigger. Between 0 and 5, 5 is bigger. And between -3 and 0, 0 is bigger. And each of these numbers is strictly bigger than the ones in column X. So Y strictly dominates X. Now let's compare Y and Z. Again, you compare the payoffs for player 2. So compare the second numbers in these boxes. Between 8 and 2, 8 is bigger. Between 5 and 3, 5 is bigger. And between 0 and -2, 0 is bigger. So again, Y strictly dominates Z. Finally, let's compare X and Z. So the first column and the third column. Look at the payoffs for player 2. So the second numbers between 4 and 2, 4 is bigger. Between 0 and 3, 3 is bigger. And between -3 and -2, -2 is bigger. Now, this time, you cannot say absolutely that X is better than Z or Z is better than X, because in one situation, X is the better response. In another situation, Z is the better response. So you cannot really compare X and Z. Okay, now strictly dominated strategies. These are just strategies that are strictly dominated by some other strategy, not necessarily all other strategies. Okay, so for player 1, uh, B is a strictly dominated strategy because it's strictly dominated by C. A is a strictly dominated strategy again because it's strictly dominated by C. And for player 2, X is a strictly dominated strategy because it's strictly dominated by Y. Similarly, Z is a strictly dominated strategy because it's strictly dominated by Y. Okay. Now, strictly dominant strategies. You see that C strictly dominates both B and A. So C is essentially the best strategy for player 1. And for player 2, Y strictly dominates the other two strategies, X and Y. So Y is the best strategy for player 2. Now, a rational outcome is when all players behave rationally. So all players play their best strategy, or their strictly dominant strategy if they have any. And they never play a strictly dominated strategy. Okay, so in this case, player 1 clearly has a strictly dominant strategy C, and so does player 2, which is Y. So a rational outcome would mean that player 1 plays their best strategy C, and player 2 plays their best strategy Y. Okay, so I want to make a note here. Um, There could be a situation when one of the players do not have a strictly dominant strategy. So let's say if player 1 or player 2 didn't have a strictly dominant strategy, and player 1 has a strictly dominant strategy, then the rational outcome is that player 1 plays the best strategy for player 1, which is, let's call player 1's strictly dominant strategy D1. Okay, so player 1 plays D1, which is player 1's strictly dominant strategy. And player 2, even though they don't have a strictly dominant strategy of their own, they must play the best they can do when player 1 plays their best strategy, right? So they have to play the best response to this D1. So basically, the rational outcome would be that player one, if they have a strictly dominant strategy, they play that, and then player two plays the best response to that strategy, which is D1. Okay, and vice versa. That is, if player two had a strictly dominant strategy, say D2, and player one did not have a strictly dominant strategy, then they would have to play their best response to this D2. Okay? And we'll go over question 4 and 5 tomorrow. And make sure you leave your name in the comment section to count for attendance. And I'll see you tomorrow.